I'm coming from the city of Haifa. Okay, yeah. And you can see here the beautiful Baha'i gardens. And I study medicine in this place. This is the Faculty of Medicine in Iași, in Romania. Back then, in the golden era, it was called IMF, now it is called UMF, Iași. And this is the hospital where I work. A few words about the medical structure in Israel. In Israel, you have hospitals that administratively belong to the government. You have hospitals that belong to city halls. You have private hospitals. And then you have several associations of insurance companies. And one of them is called Clalit. So this is a bigger organization, and it has its own hospitals. And the Carmel Hospital is one of the Clalit hospitals. You see the hospital here. I'm located not even in the main building, here in the backyard, the Department of Pathology. This hospital has 490 beds, but actually, as the Department of Pathology, we provide service not just to the hospital, but to two big ambulatory centers in the same city. This also happens in Haifa. If you are a fan of the wildlife, you are invited to visit the city. In terms of disclosure, I have no commercial conflict, but by the end of this talk, I may be in conflict with some of you guys in the audience, because some of the opinions are my personal opinions that I will present here. Who I believe may be interested in my talk? First of all, technology experts who are brave enough to tackle the complexity of the field of pathology. I encourage technological progress, but I will play here the devil advocate, because I have serious doubts about the possibility of technological progress in my field. But of course, I am a technologically challenged pathologist, and I take the risk that you, in a few years, will knock on my door and say that I am the fool who told you that you will not be successful. But maybe I'm an optimist. Who may also benefit of my talk? Medical students, computer science students, engineering students, and others, of course. And almost everyone during his lifetime will get a biopsy, and will need a diagnostic pathologist. So you may want to see what is all about, what is pathology, because this lecture will not be so much about technology, digital technology in pathology. I will mention this, but it's more like presenting the complexities of my field, so you will understand better what is pathology. And if you are interested in getting into the field and trying to solve the problems using computers and neural networks, so you are invited. So we'll begin. This is the name of the talk, Tale of a Polyp. So when I say tale, it's actually, it implies a fairy tale, right? So I would like to start with a true story. You remember the movie Star Trek, of course? And you may remember the legendary Captain Kirk, located in another galaxy. So he reached the age of 50, and now his colleagues told him that he needs a colonoscopy, okay? So after making some inquiries, he realized that there is one center that may help him, and he is interested to have this colonoscopy in that center that is located in a different galaxy. So he started moving towards the Milky Way, 1 million light years, 100,000. You see, he gets to the planetary system, okay, Earth. This is the center. Oh, sorry. Okay. Haifa. Of course, you can see the medical center, gastroenterology. Okay. So you will see that the endoscopist found a polyp inside the colon of Captain Kirk. So let's move to a higher resolution. Okay, this is the polyp. Take a section and send it to pathology. And then you see a microscopical image magnified, let's say, 40 times. We focus on this area, magnifying it 600 times. You see a nucleus of a cell, and magnifying more, there are chromosomes, and there is a mutation that we discovered, a mutation in a zone, in an area called microsatellite. So Captain Kirk was sent for consultation also to a genetician because he may have the famous Lynch syndrome. Who are the pathologists? On the left side here, you see the forensic pathology, and on the right, you see images from clinical pathology. We are not forensic pathologists who deal with autopsies, deal with crime, murders, accidents. We are on the right side. You can see every tissue that is removed from the body. It could be a mole from your skin, or a biopsy from your stomach, or anything else that is removed gets to pathology, and we are the eyes of the clinicians in the tissue. We are those who are doing the diagnosis. Based on our diagnosis, the patient is treated. So we are the judges of medicine. Everything started, of course, with the discovery of the microscope. Van Leeuwenhoek, you see, in the 17th century, and then Morgani Giovanni started to do autopsies, to trying to understand better anatomy. And then Virchow was the father of the cellular pathology. He understood, you see in the 19th century, he understood that you can understand disease by looking at the cells. Of course, the microscope was available already. And then they discovered the electron microscopy, and then Robinson Cotran are the fathers of the molecular pathology. They understood that you have to increase further the resolution in order to understand disease. So you go from cells to molecules. So the cell is the atom of the tissue. One cell is the fundamental functioning and living unit. Multiple cells will create a tissue. Multiple tissue will create an organ, and multiple organs, the body. In terms of size, where we operate, what we see, you see here the cells, 20 microns, which is a small part of a millimeter. That's what we see when we use our microscopes. So complexity. Pathology is about complexity. And this is the main topic of my lecture. I would like you to better understand the complexity of the field in order to decide if this field is of interest to you. So maybe some of you remember the Feigenbaum diagram from chaos theory. Here on the left side is order. Many times the pathologist, he knows what he sees on the microscope. So he lives in he has an orderly life, right? Sometimes it is more complex. The tissue, what he sees on the microscope is not sufficient for diagnosis. He needs to add more stains. He needs consultations. He gets positive or negative feedback from the clinician who may not be happy with his diagnosis. So the clinician may want the revision. So this is complexity. Sometimes the pathologist lives in total chaos. My boss calls me addicted to chaos because he knows that every time that I need something administrative, I need some new technology, and I don't get it because of administrative problems, I take the system to the right, to the higher complexity, and out of complexity, help emerges. So you see, the patient, if in order to make a diagnosis, sometimes we get one piece of tissue, one biopsy from the patient, sometimes we get multiple biopsies. Each one of these biopsies is processed in the Department of Pathology, and we create so-called paraffin blocks. I will show you in a moment what it's all about. Each paraffin block creates one slide or more. So you see, and these are the workers that are involved in the processing of one biopsy. One biopsy is processed by 6 to 8 people until we get to look at it on a microscope. So these are two pathologists. They are looking at a microscopic image from a tissue, and this stain, it's blue and pink, it's called hematoxylin eosin stain. And this is the routine stain. 100 years ago or more it was discovered, and we still use it. Sometimes we need special stains to emphasize special markers or special indicators of a disease or special proteins in the cell. So we do special stains. But actually, if on the left side you see, this is a prostate, you see a section from a prostate, after processing it in the lab, if you just look at it on a microscope, this is what you see. You see nothing. This is reality, okay? But we use special stains and we process the tissue in a special mode such that we will obtain something that we can interpret. For the fans of quantum mechanics, it's like, I call it surrogated reality. Not reality, but surrogated reality. For fans of quantum mechanics, it's like the collapse of the wave function. So what is the black box that allow us to transform reality into surrogated reality, so we will be able to understand what we see and to make a diagnosis? I will take you now briefly through the black box that we use in the laboratory in order for you to understand the complexity of getting from the reality to the surrogated reality slide. So this is where the tissue is obtained from surgery, from endoscopy, from ambulatory centers. You see here a pathologist, actually is a resident in pathology. He is processing the tissue. So he will take a section through the tissue. Every organ and every tissue has a particular protocol, a special protocol, according to which you have to use the protocol in order to get the section and in order to be able to process this particular tissue. And then we put a small piece of tissue in a cassette, in a plastic cassette, but the tissue is fixed in formaldehyde. Formaldehyde or formalin is a liquid, a solution that will, when you remove the tissue from the body, you have to put it immediately in this formaldehyde in order to prevent deterioration, degradation of the tissue. So the formaldehyde, of course, it's a solution that can cause cancer too. But we use it to fix the tissue and to prevent the tissue from becoming autolytic, what we call it, deteriorated. So the tissue has been fixated in formalin. Then we have to remove water from the tissue. So progressively, with a robotic machine, with a robot, we pass the tissue through increasing degrees of alcohol. Then we pour formalin. Formalin is wax, hot wax on the tissue. And then we create a block. You see, this is the paraffin block. The tissue is this dark spot here inside the paraffin block. And this is the only way we can section very thin, we can do very thin sections through the tissue, between 2 and 5 microns thick. So otherwise, if you try to do such a section through a piece of meat, it will be just wrinkled and deteriorated. You need to embed it in a medium, which we do it with the paraffin. So we cut it, we move the sections into a water bath, and we fish the tissue with glassy slides. And then we deparaffinize it. We put it in an oven to eliminate the paraffin, and then we stain the thin section with a specific, with a special robot. And then we get the slide. This is the slide, and you see the stained tissue on the slide. And then we can look, using our microscope, we can look at the slide and see the morphology, see the structure of the cells and what they produce. The cells self-organize into architectures, and then this enables us to do the diagnosis. We also have special stains for this. We can stain the tissue not just for hematoxylin eosin, but also for other markers. And sometimes the clinician wants, this process takes 1 day. Sometimes the clinician needs the response, our report, in 20 minutes because he's operating and wants to know if he removed the tumor or not from the body. So the patient is still under anesthesia, is still sleeping, and the surgeon sends us a piece of tissue, and instead of processing it in paraffin block, we do ice block. So we can speed up the technique and stain it manually. Of course, you cannot do all pathology in 20 minutes because this creates huge artifacts. It allows us only temporarily to tell the clinician that he removed the tumor, but if we want to go to many details that will help for the treatment, we need to go through the entire process that I just showed you before. We have the light microscope that we use. The light microscope can magnify between 20 times to 1,000 times. We also have electron microscopy. Electron microscopes can magnify up to, 300 times. But we really don't need electron microscope for diagnosis except for in very rare diseases where you have to look inside the cell. Otherwise, the electron microscope will not show you architectures. And in pathology, most important is the architecture and then the structure of the cells. So we use more the light microscope. So let's see, this is a patient with a lung tumor. You see the red spot here. We do a section and we stain it, we process it as I showed you before, and we obtain, you see on the left side, these spaces are the normal lung. On the right side, you see a tumor, a cancer. The thing is that this cancer may be primarily occurring in the lung, but maybe it is metastatic. Maybe the cancer was sent from a remote organ, so the cancer may be starting in a uterus or in an ovary or in a breast, and then spread through blood vessels to the lung. You see how many options you have. So morphology helps us, of course, but many times we need to use special stains for special markers. For example, we call it immunohistochemical stains. For example, we have one marker which is called TTF1. We stain the tissue, this tumor, for TTF1, and if it is positive, we know that the possibilities are from the lung or from the thyroid gland. Okay? If the immunostain shows us cytokeratin, another marker, positive, cytokeratin 7, and estrogen receptors positive, and other negative, this could come from a breast or from the uterus. So you see, we use different markers. Finally, we have to decide. We decide based on morphology using the original stain, but also based on markers. Those markers are not 100% accurate. So we, in our mind, are creating sort of a model of prediction, and we use our experience from our studies and from what we saw so far, and then we make a diagnosis. That's how the pathologist works. Those immunohistochemical stains, how they obtain them and sell them to Department of Pathology is interesting. You see, we isolate, the company is isolating proteins from different tissues, injecting those proteins into a laboratory animal. The laboratory animal, like a rat, for example, or a rabbit, develop cells, immune cells against those proteins. Then we take the immune cells, combine them by using genetic engineering with the cancer cell. So then we immortalize those cells, and those cells are injected back to the rabbit, and those cells produce continuously those immune cells that produce molecules called antibodies, and then these companies that are using this method are selling those antibodies to departments of pathology. Each antibody has on its tail a marker, and that colors the cell if the marker is there. So that's how we use immunohistochemistry. You see, this is done in robots again. Are there any errors in pathology? Oh my God. An error in pathology may lead to the removal of the wrong organ, to removal of a breast from a patient that has a benign tumor. A mistaken diagnosis of malignant will cause the removal of the wrong breast, or the removal of the pancreas or of the stomach, okay? This is Taish. She is the goddess of fortune and chance, of probabilities. Every time I get to work, I pray to Taish to decrease those probabilities of errors. For example, we have here a pancreas. You see, this is the stomach. Then you have the pancreas, the brownish one, and the duodenum, and the gallbladder. Let's say you have a tumor here, okay? And there is a technique that allows the clinician to take a biopsy, a very complicated technique, endoscopic technique, that allows the endoscopist to take a biopsy from the tumor. If I get a biopsy from the tumor, I'm happy because I can do a diagnosis, but sometimes the biopsy is from the top of the tumor, showing artifacts that may be related to the tumor or not related to the tumor. I may do an error in diagnosis. And this is another tumor. Sometimes the biopsy reaches the tumor, sometimes not. Anyway, other errors. The technician who is sectioning the paraffin block may do a too superficial section, so that will be stained. So I will, as a pathologist, get the slide with the tip of the iceberg. I may not see, if I'm not alert enough, if I'm not aware about this effect, I will do a diagnosis, and the diagnosis may be a benign lesion. But if I am aware about this fact, I can go and ask the technician to do more sections, to go deeper in the paraffin block, and then I get the tumor. But you cannot section the entire paraffin block, because your system will go bankrupt. It will be bankrupt, because every section is money, okay? So just to show you the effect of taking the small biopsy, that it is not representative. Let's say we have a photographer that is just focusing on this small area of my eye and nose. If I get it and I look I don't know the picture, I just see the small picture that the photographer took, and I show it to you, you may think you may ask yourself, it's human? Maybe not. It's Sabo. My name is Sabo. Maybe it's Trump. Maybe it's Angelina Jolie, Brad Pitt, who knows? If you take a bigger picture, which means a bigger biopsy, here you can express more confidence. You say it's human. I don't know if it's Sabo or Brad Pitt. And then you take a bigger picture, a bigger biopsy. It's only Sabo. Okay. Other errors in pathology. I show you this because if you want to use digital pathology, if you want to use deep learning to learn, automatically study the tissues and do a diagnosis, you will face these problems. Here, for example, you see only fragments of the tissue because the sectioning and the embedding and the processing eliminated part of the tissue. In this case, you see all kinds of foldings, cracks in the tissue. you get an imperfect picture, image of the tissue. You may have a problem. So the errors in pathology can be divided in pre-analytical, analytical errors, and post-analytical errors. The pre-analytical errors, an example, is the clinician. Clinician takes the biopsy, the endoscopist, send it to pathology with no information, with the wrong information. Or maybe instead of, or maybe he is mistaken in the side of the lesion. Let's say he takes a biopsy from a lady with a tumor in the right breast and the left breast. And he is crossing the biopsies, and he is mislabeling those biopsies. So I will make a diagnosis of malignancy in the side that is normal or it's benign, and vice versa. You remember, you understand what can happen, right? Analytical errors, they happen in the laboratory. You saw a lot of people are involved in the process of the tissue, okay? So a technician speaks with her friend on the cell phone, showing something while sectioning, right? She may cross between specimens. She may mislabel a specimen. The pathologist may misinterpret the diagnosis. The pathologist looks at the diagnosis, at the tissue, and instead of calling it A, he will call it B, okay? These are the analytical errors. Post-analytical errors. For example, as a pathologist, I look at a tumor in the axilla from a lady with a breast cancer, and it was a metastasis in the axilla, right? So let's say that the metastasis in the lymph node has a size of 0.2 millimeters. And I write in the report 0.2 millimeters. And the secretary types 0.2 centimeters. And I don't see it. I sign out the report with this mistake. The clinician, because it's not 0.2 millimeter, but it's 0.2 centimeters, will remove the entire axilla from the patient. So this is an example of post-analytical errors. If you want to know percentages, you see the yellow bars show minor errors. The red bars show major errors. You see, in different types of pathology, there are different percentages of errors. For example, in gynecological pathology, you can reach 9% errors. It doesn't matter if the error comes from the pre-analytical, analytical, or post-analytical. You see, lymph node system, less errors. And even there are errors that depend on the center where the biopsy was processed. In bigger centers, let's say in metropolitan centers, less errors than in smaller centers, rural centers, because of the experience that the pathologists have that work in bigger centers with seeing more specimens, right? So as a pathologist, I have to be aware. I must not be overconfident. If I do not know something, leave aside your ego. Go and show it to your friend. Send it to a different center. But we have, you see, on the right side, you have the pre-analytical errors. In the middle, you have the analytical errors. And on the right side, the post-analytical errors. We have quality control and quality assurance programs. The quality assurance programs, they focus on the process. They try to monitorize whether the process is done well, the process of getting the product, the processing of the tissue. So these are the quality assurance programs that we have. We have internal and external programs. And the quality control means looking at the product. The product means the slide that we obtain, the knowledge that the residents have, the knowledge that the pathologists have, the knowledge that they reached. These are the quality control programs that are looking for. Now, you will be the pathologist. You see the microscope in my room, okay? Now, I put a slide, and now you have to scan the slide. You see? You look just through one objective lens, and then you see the tissue at a low magnification. That's how the pathologist works. And then you start scanning it. You scan the entire tissue, hundreds of thousands of cells. You go through them, you look from far away using a low magnification, so you are getting impressed of the architecture. Your brain tells you what is the architecture, what architecture means there. And then you magnify more. You see these are structure, these are cancer, this is cancer of a colon. That's how it looks, okay? And then you magnify more, and then these are lymphocytes. You see those small dark cells are lymphocytes. And this is a tumor cell, a nucleus. The lymphocytes are the watchdogs of our body. In each one of us, so-called healthy, every day, on a daily basis, on an average, 100,000 cells become cancer. And the lymphocytes are those who fight those cells, eliminating them. After a lymphocyte is destroying a cancer cell, you see what happens here. This is called apoptosis, shrinkage and dissolution of the cell because of the attack by the lymphocyte. The lymphocyte and the cancer cells, they are both monsters, right? For example, here you have two cancer cells. There are cancer cells that will do cannibalism, that will eat other cancer cells, you see, dissoluting it. There are cancer cells that will force immune cells to swallow red blood cells, to become vampires, you see. The cancer cell is a beast, but the lymphocyte is also a beast. And the lymphocyte and the cancer cell, they are constantly trying to attack each other or trying to escape each other. For example, the lymphocyte on its membrane produces a receptor or a ligand called PD-1. If the cancer cell produces another receptor called PD-L1, the PD-L1 of the cancer cell will attach to the PD-1 of the lymphocyte, and this will paralyze the lymphocyte. The lymphocyte thinks that the cancer cell is one of us and will leave the cancer cell. That is why there is personalized medicine where we come with antibodies, molecules, that will block this pathway, releasing the lymphocyte from the magic spell that the cancer cell produces to him, and then the lymphocyte will spill fire on the cancer cell and will destroy cancer cell, you see? And this is apoptosis, what remains of the cancer cell. So, which polyp attack your colon? In terms of involving digital pathology or, let's say, artificial intelligence to make a diagnosis, you see here a series of polyps. So I'm questioning the process. I ask you, do you think deep learning will be able to understand that this is a normal tissue on the left side, this is a polyp which is not malignant and not pre-malignant, this is a pre-malignant polyp, this is actually the result of a chronic inflammatory disease called Crohn's disease or ulcerative colitis. These two, it's a higher degree of inflammation. You see, it's difficult to understand. If you are not a pathologist, it's difficult to make the distinction between the types of polyps. And this one in the lower part is a cancer. And then there is so we have normal, we have cancer, and we have pre-malignant, which is a step before cancer, okay? We call it dysplasia. What is dysplasia? You see on the left side, there is this red line. This is a membrane. And those cells that are aligned like soldiers are, let's say, normal tissue cells. On the right side, you see that the cells are still aligned on the membrane, but they lose their size. Some of them are bigger, some of them are smaller, and they are darker, the nuclei are bigger. This is dysplasia. It's a pre-malignant condition. This is 5 minutes before cancer. 5 minutes, of course, metaphorically, right? But they are still lying on the basement membrane. On the right side, they penetrated the basement membrane, they fragmented it, and they go deep in the tissue or in blood vessel. This is cancer. So dysplasia is here between normal and cancer. So here you see it's a biopsy from the esophagus. Actually, we have 4 biopsies from the esophagus here. On the left side, there is a medical condition called Barrett esophagus. But Barrett esophagus, but still not dysplastic, not pre-malignant and not malignant. On the right side, you have dysplasia. It's pre-malignant. On the right side, also dysplasia. You see you have low-grade dysplasia and high-grade dysplasia. So it means that this pre-malignant condition may get worse, but still not cancer. The complexity rises, okay? Digital pathology may solve this complexity, right? And on the right side, you have penetration of these cancer cells inside the tissue. This is cancer, right? But what are the criteria between benign and low-grade dysplasia, or between low-grade and high-grade? Because you see, if I give a report as high-grade dysplasia, in the past the patient would go through an esophagectomy. The esophagus would be removed. Today they do a more limited operation, but still is bad, right? So in this case, particularly, we don't know what are the criteria. There is a discrepancy, an inter-observer variability between pathologists. One pathologist will say negative for pre-malignancy, other will say it's pre-malignant but it's low grade, other will say high grade. So you see between 58 and 61% agreement. Let's look at these 4 images. You see these are images, these are structures from the stomach or from the esophagus, it's similar. So where do you think there is already cancer? As a pathologist, I recognize this image as an image that is totally benign, not cancer, not pre-malignant. On the right side, the same. Do you think that the computer will be able to distinguish between these? Here is 100% cancer. I believe the computer may do the difference successfully between the 0 and the 100. But here, on the right lower part, well, as a pathologist even, I'm not sure in this situation if it is cancer. I will say 70% cancer. How the pathologist thinks? Well, you know, we are pattern-seeking species. For example, this gentleman has a model that, you see, in early life, we start creating models in our brain. So this gentleman has a model of what he considers for beautiful. If he meets somebody who fits to the model, okay, then there will be assimilation, and the brain will reward us with the sensation of beautiful. How fast will be the assimilation? The brain will reward us with the sensation that it is also interesting. But if we meet something that is not in our model, there will be no assimilation, right? Not beautiful, not interesting. We, of course, can adapt, but the more mature we are, the difficult will be for our brain to adapt to new models. Anyway, the pathologist, after years of study, he studies the normal tissue, histology, histo is tissue, and the pathological one. And the brain will build models for normal and for pathological tissues. But what is the model that we use? It is mechanistic, it is mathematical, statistical, probabilistic, in order to do the diagnosis. Well, you know that there are 2 types of thinkers, frequentists and Bayesian thinkers. The frequentists will make a prediction based on frequencies, based on what he sees right now in front of his eyes. Bayesian thinker will combine the frequencies that he sees with prior information, okay? Let's say that I work for you, and in 1 year you saw that, let's say out of 100 missions that you gave me, I was successful in 90. And now you have to decide if I continue to work for you or not. So you say, oh, Sabo was successful in 90% of the missions. Yes, I will hire him for another year. But then we talked to one of my colleagues, and he said, Sabo worked for me. He was drinking a little bit. So he was successful in 40% in my case. So if you are a Bayesian thinker, you combine the frequencies from the past with what you see now, and you create a new model. So these are, of course, the fathers of the frequentist mode and of Bayesian thinkers, and we see that the Bayesian thinker is more advanced than the frequentist. So the pathologist looks at the data, okay, combines it with prior information. Prior information means age, gender, location, patient history, what we saw on the images, on the imaging, on CT, MRI. There are clinicians that try to test us. They don't understand well the work of a pathologist. They send us a biopsy with no information. He writes there, ovary. This is a problem because let's say if the patient had in the past a tumor and the clinician knows it, if he says the patient has in his history a gastric tumor, a stomach tumor, and I see a tumor in the ovary, I may think that this is a metastasis from the stomach. So I will do special stains, but I will spend less money, less stains. I will be more focused in order to reach the diagnosis. So based on the combination, Bayesian combination, of what we see and what we know from the past and our studies, we do the diagnosis. Sometimes we know exactly what we see. We say the diagnosis is consistent with cancer, and we say the type of cancer. Sometimes we say I use compatible with, which means 95%. I'm not 100% sure, but still it's a high percentage. So the clinician combines my diagnosis with his knowledge in order to make the diagnosis. Sometimes I say probably, which means 50-50. Sometimes possibly, less than, yes, and sometimes inconclusive. So that's how we operate in pathology. We are Bayesian thinkers. So far in pathology, when you say digital pathology, you refer to two big fields. One field referring to scanning the slides and storage. So this is a mechanistic approach, and more centers are scanning the slides in order to transform the real slides, glassy slides with the tissue, into digital slides. But in pathology, you have to use much more memory because one slide, one small piece of tissue contains hundreds of thousands of cells, which is much more information. So there are let's say, scanners, fast scanners, and then you have to store the information in servers, and then you store the extra information maybe in cloud, and then you can easily load those images on big screens. And if you have a powerful technology, a fast computer, you can actually replace the microscope. This is the idea. And you can share whatever you see with other centers around the world. But this is called telepathology. But, for example, in America, let's say the great experts in pathology, they don't like it. They say, as a pathologist, I am used to the finesses, to the fine details that I see that were produced by the processing in my lab. So I am very sensitive to those changes. So I do not want to see slides produced in another lab. So he said to me, send me an unstained slide and I will do the staining. Others are more flexible and say, yes, sure, I will look at your images, but I want to be sure that you scan the right specimen. So this field is still emerging. The other part of digital pathology is the AI in pathology. AI in pathology is now functioning on a very limited level. I mean, companies are, let's say, seeking to connect with our centers in order to use the big data that we scan and feed their networks and train their algorithms in the hope to develop one day a digital pathologist. By then, their hope is just to create an expert-guided system that will help the pathologist, but leave the pathologist the final decision, right? There is still more time, 10 minutes, okay, so this is a polyp, and the polyp in the colon transforms into cancer. You see that on the left side you have normal tissue, on the right side you have the cancer. So there are mutations, genetic mutations that are accumulating in order to obtain cancer. You see, for example, in order to obtain a colonic cancer, you need accumulation of 11 mutations. In order to obtain a gastric cancer, a stomach cancer, only 4 mutations. And in genetics, a mutation, when we say mutation, we call an alteration in the structure of the DNA, which may activate or deactivate the gene that will cause cancer. But there are other changes, biochemical changes, that will not alter the structure of the DNA, but they may alter the proteins around the DNA. For example, a biochemical reaction called methylation will change the structure of the protein around the DNA, and this is called epigenetic, and this also may activate the cancer or activate the gene or deactivate the gene that will cause cancer. So this is epigenetics. It's causing cancer or causing any disease by activating or deactivating a gene without changing its structure, as opposed to mutation. Mutation will alter the structure. So there are mutations that are strictly present in the cancer. We call it somatic mutations, and there are mutations that are present all over the body. These are germline mutations. The elephant is almost immune to cancer because he has a gene, many duplicates of a gene called P53. So you see that he has less than 5% chance to develop cancer along its lifetime. We as humans, we are almost reaching 50% chances of developing cancer. But of course the elephant has other problems, so he may die from other problems too. Just to add more complexity to the field of pathology, there is now the personalized medicine, because 2 tumors that look the same on a microscope from 2 different patients, one tumor may have a mutation that other doesn't have. So based on those mutations, drug companies developed specific drugs to target the product of these mutations. You see? So if this is the cell on the right side, and this is the schematic representation of the cell, this is the cell membrane, the cytoplasm, the nucleus, the DNA may have mutations. Let's say a gene becomes activated, it will form RNA. The RNA will leave the nucleus, combine with the ribosome. You know who discovered the ribosome? Palade is a Romanian scientist, right? Famous. So the ribosome, the RNA on the ribosome will produce proteins, okay? We have technology that is able to find the mutation in DNA, technology that is called FISH or NGS, next generation sequencing, or PCR. We have technology that can discover aberrations in the RNA level. You remember the step between the DNA and the proteins, also NGS. or other type of technologies. And then we have, for the proteins, we have the immunohistochemical stains that we use in the lab to detect aberrant proteins that may cause trouble, may cause problem, may cause cancer. So this is the workflow of the sequencing of the NGS, we call it next generation sequencing. Of course, digital pathology or AI tries to combine the structures that we see on a microscope with the clinical information, the prior information, and then with the immunohistochemical stains, and then with the mutations in order to predict treatment. They try to do it. In pathology, it's just the beginning. I am skeptical that during what left from my career, I will see this, but I hope it will be successful. If you want to quantitate complexity and amount of information in tissue, you can use entropy, Shannon entropy from information theory, and you can use fractal dimensions. Who remember the fractal theory? It was famous in the 90s. Anyway, entropy shows you how much information you have in a tissue. Fractal dimension shows the complexity of the structures. So here is the tissue, part of, let's say, a biopsy. You magnify this, and then you magnify again, and then you obtain 600 times magnification. This is 60, but you have to multiply by the ocular in order to get the final magnification, which is 600 times. If I compare the entropy in images in pathology with images from other medical fields, you see the difference in the complexity and in the amount of information in pathology, much, much higher. So just please let me know when I have to finish. This is a simulation that I did just to tackle, to challenge those who think to enter this field of pathology with neural networks, with deep learning. You see, this is a biopsy, the same biopsy from a stomach. You see here, I magnify this digitally. This is a very complex structure with crowding of the cells. You see the nuclei are these are the nuclei of the cells, the bluish ones, crowded and bigger. And then I'm looking here on the surface, and these are the nuclei. Here, obviously, the nuclei are darker, bigger, and more crowded than on the surface. This situation is not malignant and not pre-malignant, because on the base of we call it a mucosa, on the base of the tissue here, it is allowed to have this type of changes, but not on the surface. On the right side here, I digitally manipulated the surface here. You see, I created more crowd nuclei, more crowd, more dark, okay? If I see this in pathology, I know that this is pre-malignant, okay? If you count the entropy of these two areas, you see that there is a difference in the entropy. On the right side, there is more information than on the left side. And here on the right, and here I added more complexity, but if you do not focus on these small areas, but you calculate the total entropy of the tissue, there is not much difference between them. You understand? It's not just more information in the entire tissue. It's more information in different foci, different areas, small areas of the tissue. Do you think you will be able to tackle this? Look at what is the overlapping of the nuclei here, you see? Let's see. So this is a focus of cluster. My brain tells me how many nuclei I see here. I see 1, 2, 3, 4. But if you try to, and if I manually annotate them, you see the segmentation. But if I try to use an automatic segmentation with different algorithms, I get a wrong segmentation, right? Will you be able, you see this on the top is a pre-malignant state, and these are structures that already penetrated deep, beyond an imaginary line here. I know this is cancer. If, let's say, I ignore these deep areas, it's premalignant, it's not cancer. Do you think the digital pathology will be able to see this? This is a piece of cancer, a few cancer cells present in a blood vessel. In order for me to understand that this is invasion of cancer in vessel, in a blood vessel, which will lead to metastasis, I have to see this attached to the wall. Do you think digital pathology will see it? Look what I found here in the prostate. This is a normal, right? So, this is a core of a prostate. If I magnify this, and I further magnify this, I see here a pattern. This pattern may be one of those patterns. These are, if this pattern is equal to one of those, I call it low grade, which means less aggressive. Here I see more aggressiveness, it's an intermediate grade. Here I see more aggressiveness, it's a high grade. You see here, this is Gleason. He, in prostate cancer, realized that patterns may predict the stage. So grade predict the stage. What is the difference between grade and stage? On the left side, you see grade. It's, if you make an analogy to traffic, for example, a low grade means a tumor that doesn't look aggressive. Look at this guy, he's a friendly driver. Below, you see a high-grade tumor, more aggressive. This is a very angry driver, right? This is grade. How the tumor looks like, how aggressive it looks like, structurally speaking. On the right side, you see what the tumor produced. You see, it can have a scratch, which means the tumor was not so malignant. It didn't produce too much harm. But below, you see a tumor that produces more harm. So a low grade usually is correlated with a low stage. But sometimes, if you, let's say, if too much time lapsed between when the tumor was created and when you discovered it, so a low-grade tumor can create a real damage, a high stage. Yeah. And vice versa. Okay, so, you know, this talk I can speak more and more and more, but my point is that just one thing I want to show, one last figure that is relevant. Just a moment, please. Oh, this one. You see, before the deep learning, in the machine learning era, the classical neural networks, we need an expert to do the feature extraction and then to feed those features into the network. Today, with the deep learning, you just show the image to the algorithm, and the algorithm finds its own features, and this is the real hope for the future, also in pathology, just that pathology has been neglected because it's more complex or for other reasons, neglected by the technology so far. I hope this will change with your help. So, just I want to show you the last figure, just a moment, because this is relevant to my talk. Just a moment, please. I don't see it. That's it. Thank you very much.